Today, we are going to talk about earthengine and cloud platform. So I assume in this talk that you already have some competency with earthengine itself, but I don't assume that you have really any competency with the rest of cloud platform. So I'll be explaining some of the other tools that we have there sort of from a beginner level, and then diving in a bit to some of the tools that we have in place to use cloud platform together with earthengine. And the idea is that if you know nothing, you learn some things, and if you already know a lot, you should still find some new things to learn along the way. With that in mind, there are 3 ground rules. So we're going to cover a lot of material today. I'm going to move fast. There are a number of sections where the slides have a lot of words. You can feel free to tune those out, because the idea is not that you read those words, but rather that you have these slides available to you as a quick reference that you can use later. All the slides from all the presentations are going to be made available on the Summit website. So if there was something that I talked about and you noticed that I had the specific command you could use or whatever, it'll be there in the slides. It'll be clearer when I'm in those sections where you can begin to let your eyes glaze over. But either way, it's a lot of material, and so we will periodically, at key moments in the presentation, take a break to meditate on cute animals. I find this helps. This is the basic outline of the talk. I'm going to give an overall introduction to Google Cloud Platform, and then we're going to start talking in more detail about some specific tools. We're going to spend a bunch of time talking about cloud storage and how you can use it together with earthengine to manage your data in the cloud for various uses. We're going to talk about different ways in which you can export data and use it with the cloud. Then I'm going to talk a bunch about Compute Engine, Container Engine, and a number of other cloud platform services that people like to use together with earthengine. And then finally talk a bit about kind of the state of the art and where things are going with TensorFlow and machine learning in the cloud. And before we begin, we can meditate on our first cute animal. So, cloud platform. For the past 19 years, Google has been building out the best data centers in the world. We were in many ways the first cloud computing company, but we were different in that we were entirely vertically integrated. So we had to build out the best data centers in the world in order to power the services that you think of as Google search and ads and so forth. The data center tools that we needed to exist didn't exist in order to build those products. And so we had set about building the world's best data centers. We were a little late in the game in realizing that that itself would be a great product we should sell, which we've been shifting to doing. And it's been very exciting. But I want to begin by talking a little bit about the data centers themselves. These are some of our engineers at one of our data center sites. They like to go ice fishing in the ice outside the data center. You may be wondering why our data center is in a place where you could go ice fishing. And the answer that I think is particularly of interest to this audience of people, more than the average cloud computing customer, is that we're very, very concerned about renewable energy and energy efficiency of our data centers. So when we go to a cold place, we can take advantage of natural cooling of our data centers, which helps us bring one of the big contributors to the overall inefficiency of data centers way down. We've been carbon neutral since 2007 through efficiency plus offsets. And then this year, we announced that we finally reached the goal of being 100% renewable for our 2017 cloud computing energy costs. So if this is something you care about, you can know that if you happen to bring your workload to our cloud computing environment, you too will be taking advantage of 100% renewable energy. It really all began, as I was alluding earlier, with search. Search is just a ridiculously large-scale web application that required us to build ridiculous data center technology. Many of the technologies that went into that are technologies that Google has published papers on over the years. Going back to early papers early in the millennium around technologies like the Google file system and MapReduce, and then some of the newer technologies going up to more recently technologies like TensorFlow. We have a real kind of academic bent to us as engineers at Google. We like to publish these papers. And we were happy to see that, with a lag of a few years, many of these technologies also became flourishing open source communities. So the core technology of MapReduce became, a few years later, the open source package Hadoop. and so forth. This has been a continuing theme which we've really enjoyed watching. We really get a kick out of comments like this from Doug Cutting, the co-creator of Hadoop, who said, Google is living a few years in the future and sending the rest of us messages. It's fun to get to employ a lot of the world's top computer scientists who get to push these boundaries, and fun to see other people picking up on the technologies that we release. But what we began to realize was that that gap between the technology being invented at Google and then entering the outside world was sort of an unnecessary lag in the system. There was an opportunity there for us to revolutionize the cloud computing world itself by taking those technologies and making them available externally. And so we started doing that, and you start to see some of these same core technologies powering some of the really interesting differentiating products in the Google Cloud Computing family. So if you just need storage or you just need virtual machines, you can come to Google for those, and we'll offer great features at a great price. But what really makes Google's cloud different are some of these higher level technologies that don't have an analog elsewhere, because they represent a much tighter loop between the invention of really revolutionary technologies and then their implementation in a product that you can use yourself. So we have lots and lots of cloud products now. These are some of the big names solving problems related to storage and databases, solving problems related to big data analytics, and most recently and excitingly, solving problems relating to machine learning. I'm going to talk about a number of these over the course of this talk. And a fun fact is, Google has been known for having sort of billion user scale products, and just in the past months, cloud became one of them. This is a big, big bet for us. We have a ridiculous number of users who are, I actually don't remember exactly how this is qualified in terms of what that nature of that usage is, but cloud is reaching 1 billion people on the planet. And it's, if you listen in on our financial statement phone calls, this is a huge area of investment for us. People sometimes express questions about, is this just sort of some flash in the pan? This is really Google's big bet for the future. We've been looking for a long time to find what is, after advertising, the next bet that's going to carry us financially forward as a company. And by all the numbers, it's clear that cloud computing is that. So we have an international and growing network of cloud computing data centers available to you. So the purple ones here are currently available regions. The cyan or blue or whatever color that is, pins represent new zones and regions coming online. This slide may, for all I know, be slightly out of date. Some of those may have already come online. I've not been following every single one because there are a lot and it's growing fast. A lot of that's in demand, in response to customer demand to be able to locate data and computation in specific regions for either latency or regulatory reasons. And on top of that, we then have the just most ridiculous global network for moving bits and bytes around. And that includes both our own private backbone for moving data between data centers. This is a big differentiator for Google relative to many other, or the other major cloud providers who rely for many of these key backhaul segments on sending data over the open internet. We have our own private fiber that we operate between all these data centers. And then we have, for example, hundreds of edge cache locations that you can now take advantage of for serving data on popular websites. And these are all technologies, again, that we had to build out to support our own products. So why do we have a ridiculous global network of edge caches? YouTube is a great example. Being able to move those videos around the world and serve them efficiently relies on us being able to place videos that are popular in one country next to that country. So we're able to offer these services that are built on a deep history of building our own products on top of these technologies. So just to give a hint of what's going on under the hood, we build our own everything in our data centers. The Jupyter cluster switches allow us to move data within a rack at something comparable to millions of high-speed home internet connections, right? This is not like networking a bunch of computers in the usual sense. And in fact, a better way to think about this is that a data center is not a collection of computers. It's really a computer. The fabric between those individual machines within the data center is so rich that you can begin to think about it as more like a computer. Modern data centers blur what had been historical lines between data center style computing and supercomputer style computing, where you had a rich interconnection fabric between all the nodes. We're able now to play the kinds of games that you used to be able to play only in a fully connected supercomputer, now in a much, much larger and shared data center environment. Another example of that kind of fully integrated engineering and what it's able to offer, since we're building our own network architecture, we can do things like integrate special hardware support for security and authentication directly into these individual machines. So we have the world's best, at least in the private sector, and I would say, in my opinion, the world's best computer security team on the planet, building security first throughout our entire stack. And that's to support the privacy of our own users, and which obviously is very important to us, because if our privacy, if our own products are violated, that's a big privacy nightmare that we don't want, and we can share those same technologies with you if you're building on top of our stack. So, in summary, or to sort of capture the way the trends are moving, in the beginning of distributed computing for the masses, the model was you bought a cluster, you had a colo, you managed machines. And everyone realized that the CapEx costs and the management costs of managing machines and managing then heating and power and all cooling and power and all this for the machines was a nightmare. And so everyone moved to virtualization. The idea was, okay, now you didn't have to operate the physical data center, but you would have a virtual data center that you could just turn up on demand and scale and shut down as you needed. And that still is the way a lot of cloud-based services operate, but we're seeing a really exciting shift towards a serverless architecture. And EarthEngine is a great example of a serverless architecture. You show up, the data's there, you run some queries, you're not thinking, oh, I need to provision 5 VMs that need to have this many CPUs, this much RAM. All of the overhead of managing even a virtual data center is gone in a serverless architecture. And the idea is that this allows you to focus on what had been, this chart suggests it's an eighth. Our preliminary work a number of years ago looking at remote sensing research labs suggested that it was actually even less than an eighth of people's time was going to the real science. It was all going to data management and cluster management and all these things. So in some labs, it was clearly like a 90% overhead that we've been able to help remove. And this is something we've actually been able to quantify recently, not for EarthEngine, but for another product very much like it in Google's cloud, which is Google BigQuery. I'll say a bit more about it later. It's a tabular sort of SQL engine. But ESG recently released a white paper where they had done some surveying of BigQuery customers and found that these commercial customers could expect to save on the order of $1 million over 3 years just by using BigQuery instead of managing a conventional Hadoop cluster themselves. And that's all because of these overheads, just human time spent to managing even virtual systems versus having a system where you just show up with your data and your SQL query and you run it and you're done. So we're very excited about this sort of serverless direction in cloud computing. So, a few details in case you are brand new to Google Cloud. These are the practical things that you will encounter when you start to use Google Cloud. In cloud, all of your use of the platform is grouped up under what are called projects. So when you first sign up, you'll create a project. You can create projects for yourself. You can create projects for your organization. This is the unit of billing, typically. In other words, for a given product, if you need to apply your credit card number, it'll apply to all the charges under that project, which is one reason why you may end up with multiple projects if you want different things to be billed to different credit cards or what have you. But all the resources within a project are designed to work easily together. Authentication within that project, for example, is typically very straightforward. For some of our services, in particular the kind of phase 2 services, the non-serverless services, you do get to decide where you're putting data or computing. And so this is where the idea of a region and a zone comes into play. So if you are just running VMs in the traditional way, for example, you'll get to decide where to place them. The region is sort of like a continental or subcontinental scale. And then within each region, there may be multiple zones. And these zones may have different characteristics. In particular, if something goes wrong, which is rare but does happen, it's typically contained to one zone. So there's some advantage to distributing your data across multiple zones if you're building an ultra-high availability application, for example. And all of these regions and zones have little tags like Asia East 1A. That's a particular zone in Asia East. And if you don't use, if you only use these serverless higher level cloud platform services, then you get to not care about any of that. So if you're just using earthengine together with cloud machine learning engine or something like that, you don't need to care. It's only if you use sort of lower level services that you get to care. All that is managed in a couple different ways. There's a console at console.cloud.google.com where there are UIs for managing all the different cloud products. So you can do many things directly from the UI, many management tasks. You can also just use it to keep an eye on all of your cloud computing services that you have running. There's a fun thing that launched recently called Cloud Shell. This little GIF is walking you through it. It'll loop in a second. There's an icon on the top right of the console where you can get a little shell running in your web browser. And what it's doing here is behind the scenes is provisioning a very small VM for you to use as a sort of entry point into the cloud. So a common thing people do in the cloud computing environment is they manage one machine just to be their kind of admin machine. And now you don't even have to do that. It's sort of set up for you automatically. You can just log in, and you're instantly in an environment that is credentialed to manage all of your cloud services within that cloud computing environment of yours, within that project. So this is, if you're doing some of the tutorials, for example, that we have on the web about how to use Cloud Data Lab, say with earthengine, a lot of them now take advantage of this as a quick and easy way to help set up whatever other services you want to run. Get a lot of questions, of course, about pricing. We have a handy pricing calculator that you can use. One thing that's happened in the last year is that we have established free tier pricing for a number of cloud services so that you can actually get started without having to think about the pricing at all, as long as you're confident you're within kind of that free tier. I'll comment on that as we talk about some of the specific products. But you can use the calculator to answer questions about how much your various scenarios are going to cost me. And if you are in the nonprofit researcher public benefit arena, we do have a cloud credits program that might be able to cover your costs. So there's an application form, and there's a link to it also right off the Summit website where you can apply for cloud credits to cover your use of cloud platform in your public benefit research project. All right, so that is your sort of high-level marketing spin-heavy intro to cloud platform. We're now going to dive in, after meditating on this sand kitten, to Google Cloud Storage in particular. I'm going to have some water. OK, so cloud storage. This is kind of what it says on the tin. It's a data storage service. It's durable and highly available object storage, which is really just the same thing as file storage in the cloud. You can also use it to serve those files or those objects on the web if you're building web applications. We offer several different storage types. This is just trading off certain characteristics that you want your data to have versus price. They all use the exact same API. So the four types that we currently support are, as you can see on the screen, they range from the one extreme, the multi-regional bucket, where you can put your data, and it's available for high QPS serving in a large region of the world. So that's sort of our most highly available, low latency, expensive serving option, all the way over to cold line, where we take advantage of some unique characteristics of our data center storage architecture to provide extremely low-cost storage for data that you know you're not going to be accessing more than about once a year or so. So this is a great place to put archival data where you can have access to it faster than a more conventional tape-based solution, but at a similar price. And sort of a range of options in between. So for large data processing workflows, the most common choice is the regional, where you're going to be placing your data near some computation and hammering it with your reads for computer analysis. And the idea here is that objects is what we call files. It's the same thing. And you store them in buckets. So you can think of this almost like buckets are the top-level directories in your file system. And each bucket can have a different configuration in terms of the type of storage, in terms of the default ACLs. That's kind of the unit of configuration for many of these defaults, billing as well. And then there are these cloud storage URLs that start with GS for Google Storage that are how we refer to those objects internally, even if they're not being served on the web. You'll see those used in our APIs and command line tools. Buckets do live in a single global namespace. So that is to say, if you go get a bucket and then you go along and want the bucket with the same name, you lose. So generally, you want to include something uniquely identifying about you, your company, your project, to minimize the chance of confusion down the road. It's almost like getting a top-level domain name. I'm not going to go get the www.science.com domain name just because I want to go do some science. I'm going to get a domain name that reflects the particular science that I'm trying to do. So objects can be either public or private, so you can use this for storage of your own data for your computations, or you can use it to serve data publicly on the web. You manage all that at a pretty fine grain using access control lists, or ACLs. And that's just a fancy way of saying you can grant reader, writer, and owner permissions on objects to users or groups. One concept we'll encounter later that's very important is the idea of a default ACL. If you're about to go create 1 million objects, for example, as we'll see later, map tiles that you want to render and then serve on the web, you want to get the ACL right, set right on those 1 million objects the first time, and a default ACL is a great way to manage that kind of thing. Within the Cloud Console, each individual cloud product, including cloud storage, has its own little sub-console. And you can use this UI to create and manage buckets, upload and manage objects. It's pretty basic file system management stuff in that console. The way the pricing works, you can do the math on this for your own use case. I'll go through a specific sort of case study in the next slide. But the basic idea is that the storage amounts vary based on the type of storage. And then there's pricing per query. And it's a much lower price for just the queries that are basic read operations. Higher price for queries that actually involve managing or mutating the data in some way. And then one price that's important to bear in mind if you're serving data is egress bandwidth. So that'll vary depending on where your end user is. Egress means bandwidth out of Google's network into the open internet because you're serving data to someone else somewhere. And depending on the nature of where you're serving that data, the cost to Google and therefore the cost to you of that bandwidth can vary somewhat significantly. So if you're building a website, it's something to think about. So as a okay, there we go. Weird. Right. One comment here is that there are now free usage limits. So you can get 5 gigabyte months of regional storage to start playing with. And so for serving some small content on a small website that's not going to get thousands of users, this can be sufficient. It's also sufficient to at least start playing and figure out what your real costs are going to be based on measuring actual usage. So pricing case study. Suppose you are doing a large Earth Engine analysis, and it's a global scale analysis. You're going to produce some visual result. So you want to make map tiles for the entire world at Landsat resolution. We've done this for a number of projects. We have a sense of how much data is involved. You can do the math on it too. It turns out to be about 100 gigabytes. So if I'm serving this on the web, I might pick my multi-regional storage, and that works out to about $2.60 a month. If you imagine this gets some amount of traffic, this is not going to be maybe New York Times blog amounts of traffic, but an ordinary amount of traffic for a niche scientific website. That might be on the order of, say, 1 million queries a month. That's about $1, and the bandwidth for that, it'll vary by the exact distribution of where your users are, but it's, again, on the order of $1 a month. This whole thing, serving this layer out, costs about $5 a month. So for many realistic uses, the prices that we're talking about here are absolutely negligible. Now, that doesn't mean you couldn't come up with use cases that would be much more expensive. But my point is that you don't necessarily have to become panicked just because somebody's asking for your credit card on one of these as you're signing up. A lot of these use cases are quite cost effective. So if you make an object public, there's just a simple way to construct a URL to it that you can then serve that in your website. And there is a sort of slightly funkier way that you can actually serve even private objects within your web application if the end user is logged in and has rights to that object. This involves a redirect dance, and it's not ideal for public content, but it works. If your content really is public, mark it as public, use the public serving path, you'll be happier. Now, if you really are serving a high QPS web application, maybe you really are expecting this to get substantial amounts of usage. One exciting new product we have is the Cloud CDN. It's a content delivery network. This takes advantage of that same multiple hundreds of edge cache systems that we have around Google for caching our own content. And the way this works is you end up paying, if your web application is mostly serving the same static content to most users. So the cache hit rate, we call it, the likelihood if a user is requesting a given object that's already in the cache, if that's high, then it can be much, much cheaper to serve that out of the CDN, out of the local edge cache, versus serving everything directly out of cloud storage. So this takes a couple steps to configure. You configure this thing called an HTTPS load balancer to point to your bucket, and you configure the CDN to point to that. It's a couple steps. There's some tutorials on the web. You don't want this for your average small website, but I know we all have aspirations to build the next incredibly popular website, and when you get to that point, this is how you can scale without... Yeah, Pokemon science, sure. All right, so that's your introduction to cloud storage. And I want to dive in a bit to how you actually use that, what the mechanics are of using cloud storage together with Earth Engine for some of these use cases after we meditate on this cheetah cub. So, there's a tool, if you install the Google Cloud SDK, called gcloud. It's a command line tool where you can manage most of your cloud services. There are also, for a few particular cloud services, additional tools that come with it. And gsutil, the Google Storage Util, is one of them. They come bundled together. So just go install the Google Cloud SDK. You'll get them both. And you can use these to copy data up, manage data. You also use gcloud to manage your virtual machines, lots of other things. And if you do use the Cloud Shell that I mentioned, where it's a web-based terminal, it comes pre-installed with these things, so that's another bonus. And Earth Engine has its own command line tool. Thank you, Ali. Thank you, Chris. Earth Engine has its own command line tool that you can use to do the same sorts of management operations or for your Earth Engine assets. So as of, for example, today, this includes, if you install a fresh copy, the ability to upload a shapefile into an earthengine table asset. And this one comes with the earthengine Python SDK. So it's currently distributed separately, but they're easy to go get them both. And if you follow, again, any of the tutorials for getting started with earthengine, you'll have easy instructions for how to do these things. So here's a simple example of using the two of them together. Now we're getting to that point in the talk where the important thing here is just the concept of what can be done, and you can come back and copy and paste from these slides in the future if you actually want to try these things. Don't worry necessarily about reading every word on these slides. But the idea is that it's a pretty simple two-step operation. If what I have is a large image that was maybe distributed as a bunch of geotiffs, and I want to get that as an asset in earthengine, this is an easy two-step dance. You use the gsutil tool first to copy all those files up to Google's cloud. It's just like copying files around your own local network, but with a little prefix that says do it in Google's network. And then an earthengine command to upload all those geotiffs into an earthengine asset. And here we're actually doing this as a two-step dance. So here we're actually running the gsutil tool again to list all the images so that I can pass all of them in to the upload image command. And so pro tip, if you aren't familiar with this trick, these are back quotes. And what they mean, if you're using bash or a sort of similar Linux terminal, is run that command and take its output and stick it right there on the command line as additional command line arguments to the next tool. Here, the earthengine upload image command takes a list of cloud storage URLs. So here we're generating that list of maybe it was 1,000 files that make up this maybe large image. So you don't have to think about what those are. It's a little common two-step dance that I often find myself doing. You have then all of the sort of basic file management tools, and they feel very similar between these two environments, managing your raw files in cloud storage and managing your assets in earthengine using the earthengine and gsutil tools respectively. So you can list and copy and move and delete in more or less the same way in both. We designed the earthengine command line tool to feel as familiar as possible to existing users of the gsutil tool. And so you can also create folders and buckets using these tools. So in gsutil, the thing you create are cloud storage buckets. In earthengine, you can create folders, and you can create image collections. So in case you're not familiar with the distinction, a folder is just like an ordinary directory. It can contain anything. An image collection contains only images. It's got indexes that let you do fast queries against the images in that collection. You're ACLing everything in that collection together. It's a way of creating a bundle of images that you want to compute on together. And let's see, we already talked a bit about the earthengine upload image command, but we can dive in a little bit to some of the options that are available. In particular, when earthengine ingests an image, we always are building a pyramid of lower resolution versions of that image that you can use when computing and previewing tiles, and you can control exactly how that's done. So by default, we're taking the mean of 2 by 2 squares of pixels, but that's not appropriate for certain types of data, in particular sort of classifications, where the mean of two values does not necessarily represent anything meaningful. So you can specify a different pyramiding policy. And you can specify things like no data value, or the last band should be used as an alpha channel. And this lets you control the masks within earthengine that earthengine applies to your data. And now, of course, you can do the same thing with earthengine. With tables into earthengine. Today, the only file format that we support is shapefile, but we've got a bunch more coming soon. Please express your desires so we can prioritize them accordingly. And the way this works, if you're using the command line tool, is you specify the path to the sort of master file, the .shp file. But all the other sidecar files, if you've got a shapefile, it comes with multiple files. They need to be there too, and we'll use them automatically, just based on them having the same base file name. Once you've got your assets in earthengine, you can use these tools to manage the metadata on them. So you can set, for example, the timestamp on all the images in an image collection, and that will allow you to do efficient filtering of that image collection using the indexes that we build. And you can dump all the properties as well. Again, I'm not going to dwell on all the details here, but you can look back as a quick reference. And I should mention that if you just run earthengine-h, that's the help, and it'll give you a list of commands. If you run earthengine, some command.h, it'll give you more help on that command. So all the reference docs are kind of built into the tool. Anyway, managing access control lists. So if you have data that you want to share with your colleagues or make public, you can again do that very similarly in these two worlds of cloud storage and earthengine. And you can do fancy things. These are just common patterns that I'm going to leave here for you to reflect back on for things like copying an ACL from one object to another. All of this works the same in the earthengine and cloud storage worlds. Oop. And lastly, in this category, you can use the command line tool to manage long-running earthengine batch tasks. So that includes uploads. It also includes exports of various types. And you can just keep an eye on them here, much like you can in the tasks panel of the code editor, but now at the command line, in case you are the sort of person like me who likes to live on the command line. All right, so bearing this hedgehog in mind, we will dive in a little bit more now to how you can export data from earthengine to cloud storage for use in other cloud computing workflows or for publishing on the web. There are a few different types of data that you can export. Again, don't worry about every word. You can use these as templates when doing your own exports. Exporting images directly to cloud storage works like this. You specify the image, you say where in cloud storage you want it to go, and you specify things like at what scale or in what projection or what spatial region do you want, and earthengine will go compute, if needed, the data and package it up as one or more geotiffs and write it to cloud storage. One thing that we added in the last few months is a bunch of options here that give you much finer control if you're exporting a very big region over how that's going to get chopped up into geotiffs. So I was just using this a month ago when we were exporting the most recent version of the Hancher global forest change map. We wanted a global tiling where every TIFF was going to be exactly 10 by 10 degrees. So I could set that up easily as one export now, as opposed to having to hand build one export per tile using some of these new features. And you can do the same thing in Python. This is what it looks like. In fact, this is, I think, more common for people who are automating these sorts of tasks to be doing it in Python. One little trick to point out that works a little differently between Python and the code editor. In the code editor, you run your export, and then you go over to the tasks tab and press the run button there. In Python, the equivalent of that is that these functions return a task object. And when you're really ready to start them, you run task.start. It is easy to forget that step if you're new at this and think that you're going insane. That is what's wrong. Been there. Tables, similarly to images. So this is useful if you want to publish these sorts of results, say in conjunction with some scientific paper, and you want to use cloud storage as a serving platform. This is also useful if you just want to get a table of data to then bring into some other processing pipeline that is not powered by earthengine that happens to be running in a cloud or elsewhere for that matter. So right now you can export CSVs, GeoJSON, KML, and KMZ. And again, you can do this from JavaScript or Python equally. Video is a particularly fun one that I'm not really aware of anyone else doing this quite the way we can, where you can specify an image collection where each image is one frame of the video, and we'll render up a whole MPEG for you. This is fun. Great for building visualizations on the web that really convey a sense of change. And the time access in the video doesn't need to correspond to real time. You can vary some other parameter and make a video out of that. And then finally, the set of things you can export is map tiles. The main use case here is serving visualizations on the web. So we can go build a whole pyramid of Mercator map tiles, pre-compute them for you, put them in cloud storage, and then you can stick them on your website. So we make a whole folder hierarchy of the map tiles in cloud storage, and next to it, we stick a simple HTML and JavaScript application that is sort of short enough to be intelligible by even a complete newbie in the HTML and Maps API world. And you can use it as an iframe. You can embed that directly in your website, or you can use it as a starting point for building some larger, more complex application. This is an example of just what it looks like. So all it does is it puts a map together with your tiles that you ask to be exported, and a little zoom box, and just very basic Maps API app. And yeah, that's the entirety of it, the auto-generated. So you could go in, and if you just wanted to say change the default viewport, if you want to use this as an iframe, or some simple change like that, you could just edit this file that is automatically generated and get a tweaked version of your exported map. Or you can skip that entirely, ignore the HTML and JavaScript file that we make, and just use the map tiles. Maybe you want to use some completely different viewer that can accept Mercator map tiles that have been pre-rendered. Great, they're there in a simple, predictable naming scheme. And you can use the cloud storage browser to view them. This is a great example. Well, we'll come back to that. In fact, very specifically for your reference, the map tile path is wherever you said /z, which is the zoom level, /x/y, which is the position within that zoom level. They're all in this Maps Mercator projection, which is at this point used by most 2D mapping applications. So you can control the file format. So there are two main file formats that get used for map tiles on the web. Most of the time today, they're PNG and JPEG. The advantage to PNG is that it supports transparency and it's lossless. So that can capture fine details that get lost by JPEG, which does not support transparency and is lossy. So why would anyone use JPEG? The reason is that they're much, much smaller. It can be a factor of 10 smaller. And this can have a really profound impact on the feel of your website, especially for somebody who's not on a super fast network. But actually, some of these pings can become large enough that you notice the slow loading, even on a reasonably fast network. So this is just a choice that you have as a web application developer to trade off the performance of your website against the visual quality of the maps. Yeah, question?
The time lapse. This is a video, right?
Yeah, the time lapse is a video. So that's.
Video exported to do?
Yeah. So the question is, what's the deal with the time lapse, the global zoomable time lapse? It's kind of a hybrid of these two technologies. It is a pyramid, but not of static map tiles. Instead, it's a pyramid of video tiles. So they're produced using the same video encoder that you can use. But we don't currently have, and it's been on our list for a while, and we just need the right killer app to get us to get around to it. We don't currently have a way for you to automatically export a whole pyramid of video tiles. And it's just, again, awaiting the right use case. So you could use that video exporter to export a whole pyramid of videos and then use the same open source viewing software. But it would be a little annoying because you have to manage a large number of exports. But that uses MPEG. That's a time domain lossy encoding that's designed to let you bring not just one image, but a whole stack of images to the browser in a reasonable time frame for the user to wait and view. So that's even sort of further on the lossy compression direction. Yeah, you can export a video, and it will be very similar to those videos. So the one, I think, last comment to make on this is a great example of how you want to think ahead about permissions when you're exporting potentially 1 million objects. If you get the permissions wrong and you need to go back and change the ACL on 1 million objects, you are going to be a sad panda. You are going to be happier rerunning the export at that point than actually trying to go fix the permissions on 1 million objects. So there are two ways this works, and there's an option on the exporter in earthengine. If you're the owner of the bucket, then you have permissions to actually set the ACL explicitly on each object as you're writing it. And this is a common case. And you can get that by specifying write public tiles is true, and that's the default behavior. So if you are the owner of the bucket that you're writing to, and your purpose is to serve this stuff on the web, you're good. The defaults are going to work for you. But if you're not the owner of the bucket, then you can't control the ACL of each object as it's being written. And so in that case, you switch write public tiles to false. And what it will do in that case is it will use the default ACL that the bucket owner has configured. So sometimes you end up in a situation where someone doesn't want to give you owner permissions on a bucket, but they do want you to write some data into it. And then you just need to negotiate with them to get the default ACL set correctly before you write it, or you will end up in the sad panda story. I just flagged this because the potential sadness, if you get it wrong, is relatively high. OK, squirrel. So I think we're done talking about data and exports and imports, and we're going to move on to talking about computation, how computation works in Google's cloud platform. First, by talking about what I might call the classic or kind of second wave offerings, where you are thinking to some degree about virtual machines, and then moving on to even the higher level computational services where you can not care about that at all. So Google Compute Engine. These are traditional virtual machines that happen to run in Google's data centers. So you can easily bring up new ones, scale your jobs. We have an unusually large range of configuration options for those machines compared to some of our competitors in terms of the number of CPUs, amount of RAM, and so forth. You can get pretty good pricing if you happen to be able to tweak the requirements to match your actual needs. One nice thing is that long-running workloads are automatically discounted. So if you've got a VM that's just sort of always running, that's a little cheaper than that same VM per hour going up and down all the time. And again, this is now powered entirely by renewable energy. Yay. Yay. One other comment, I guess, in addition to the automatic discount of long-running workloads, there's a concept that I think I may talk about earlier, but just in case, which is the preemptible virtual machine. So this is a really exciting offering that we have where if you are running a batch computation workload where each individual worker can tolerate being shut down or being put on pause for a moment, you can use preemptible VMs. These are great for large parallel batch computations, and they are much, much cheaper. It turns out that as we're playing this Tetris game of getting everyone's jobs running in different machines, the advantage of being able to shut down or move around your job is so great in terms of our ability to solve that optimization problem that we can pass on a lot of savings to you in those cases. So if you're doing batch computation and you're not using preemptible VMs, you should probably do that now. Big, big cost savings. It takes a bit of work to make sure your job actually can tolerate being preempted, but it's totally worth it. So why would you use Compute Engine and earthengine together? There are two main categories of reasons that we see. The first is you've got some third-party binary, some legacy tool that already exists that you just want to use with your data as part of a workflow that also involves earthengine. So you can run it on Compute Engine, and there's some moving of the data back and forth, but it allows you to build a kind of hybrid solution to your problem. And the other reason is because you just need some place to run your earthengine scripts. Say you're building an earthengine-powered website, and so you want to run a web server built in Python, or some other automated processing environment built in Python that happens to drive earthengine. You can run that in Compute Engine. And the idea here is the data never has to leave the cloud. Even if you are doing imports or exports, they're actually all within the cloud. That's much cheaper. It's much faster. And so you can use cloud storage as a staging area for moving data in and out of earthengine, for processing it in your own third-party tools. I think an important point that, in my opinion, cannot be emphasized enough, and my guess here is that you're all already converts. You're all believers, but it's worth emphasizing. If you look at the trends in cloud computing and in computing generally, everything is going exponentially up and to the right, or down and to the right, depending on what you're talking about. Costs are going down exponentially. Data volumes are going up exponentially. But the exponents, or the bases of the exponents, they differ. And so as you roll the clock forward, certain terms are getting dominant more and more and more and more. And the term that is really dominant from a cost perspective is bandwidth at every level of the system. The more you roll the clock forward, the more bandwidth is the limiting factor. And long-haul bandwidth into and out of a data center is one of the places where that hits you the most. So the more you can do everything within one environment, the more you're going to be able to avoid paying for exponentially growing bandwidth costs relative to everything else. So you will be unsurprised to learn the compute engine has its own little console within the Cloud Console. You can use this to manage almost everything, start and stop instances, so keep an eye on them. Lots of different configuration options here. And you can do all that stuff from the command line tool as well, from the gcloud command line tool. Once you've got your compute engine VMs up and running, there's a quick start for doing that. And then you can install the earthengine SDK. And this is here for your copying and pasting convenience in terms of just installing all the prerequisites that you need in order to be able to install the earthengine SDK. If you're totally brand new to running VMs like this, one of the realities of life, if you're using sort of the bare metal VMs, is that it's like getting a brand new machine. You got to install everything the first time. This is one advantage to moving to container-based models, which I'll talk about in a second, is that you can kind of do that once. Anyway, that's your copy and paste option there. So when you are running in a VM, you've got some options for how you authenticate to earthengine. In particular, this is a little different from how you might use other cloud tools within cloud. Because earthengine is partly a cloud tool and partly like a web UI that's almost more like a consumer tool. The code editor can feel more like you're using Google Docs. And so there are reasons why you might want to authenticate as yourself, which is something that you normally don't do in the rest of the cloud computing world. So if you want to authenticate as yourself, meaning your Gmail account or whatever account you're using, its credentials, then the earthengine command line tool has an authenticate command you can run that will then let you authorize it to use your credentials specifically for earthengine and earthengine-y stuff, and it'll store those credentials on your VM. And then the alternative is to use a service account. This is the more common way to do cloud computing-y stuff in the cloud. When Google sets up your VM for you, it will automatically create a service account, which is just like a special account that does not correspond to a human, but that is allowed, has the authority to act kind of on your behalf within that project, and you don't have to manage credentials as a result. The reason that you might not want to choose to do that is just that there are parts of earthengine that are very much have a foot in this consumer world where when you're logged into the code editor, you're logged in as you. So you might want your automated tools to have the same credentials. So these are just sort of templates for your reference. But basically, if you want to use your own ordinary Google account, you can create, this is the command line example for how you create a new VM. You can log into it and then run that earthengine authenticate tool command. So you'll notice when you're creating a compute engine instance, you get to decide what do you want to call it. You get to decide what the machine type is. F1 micro is the kind of very small compute engine machine. That's a great size for if you just want a machine to run scripts that are puppeting earthengine from. It's not designed to run real computation on that machine. And the nice thing about that is that that's also now where the free tier is. You can get a free F1 micro machine. So if all you want to do is have one of these to puppet earthengine, that's all within the free tier. And you can specify then where in the world you want to run that VM. And once you've done that, then if you're in Python, you can just run e.initialize, and it will automatically grab those cached credentials. No more fussing with credentials at that point. Alternatively, if you want to use the automatic service account mechanism, if you want to do that with earthengine, there's one thing you have to do a little differently. earthengine currently uses a different, what we call authentication scope than the rest of Cloud Platform. This we hope will change over time, but for now, this means that when you create your compute instance, you have to tell it what scopes you want that account to be able to access. And so you tell it both the standard Cloud Platform scope and the earthengine scope. And so that's one little step when you're first creating your instances, your VMs. But then once you've done that, you can use the standard Google credentials library to get those default credentials. And again, you're not having to manually manage the service account files. You're letting Google manage it for you, and you'll get credentials that have the right scope. If you do that, as with any service account earthengine application, you do have to currently talk to us to get your service account whitelisted for earthengine access. So there are a few ways to find it, but this is one way you can find what is that service account. And in this example, it looks like this. And you can send that to us, and we'll just add it to the earthengine whitelist on your behalf. So pricing for Compute Engine varies entirely by the size of the machine. So this would be a very, very large matrix, but I just picked out a few representative examples. F1 micros, they're priced at a level where you can just run them, forever, and it's like $4 a month. So that's in the don't care zone. Running a sort of standard one-core machine, so this could accommodate real small computational workloads. Now you're at the point where running that for a full month is $25. So depending on your lab, that may or may not yet be above the don't care threshold, but you can always fall back to running them only as needed, and then you're paying an hourly fee. And then as you go up to larger machines, even by the time you're at a 16-core machine, running a 16-core machine forever is like renting a 16-core machine in the real world, in terms of the number of zeros involved. So at that point, you might prefer an on-demand hourly model question.
You said hourly fee. If you run it for 5 minutes, do you pay for 5 minutes, or do you pay for an hour?
Yeah, the granularity is sub-hour, and I honestly forget exactly what the granularity is. It's not 1 second, but it's not 1 hour. It's somewhere in between. The docs will say more about that.
You
Yeah.
mentioned the free F1 micros.
Yes.
What is that referring to again?
You get.
Cheap enough where you consider it free?
No. I mean, there is a free tier now, so that if all you want to do is, then there are some other constraints you can go read about, but basically if all you want is your one F1 micro, that is actually free, it's been a long and slow process of setting up the free tiers properly for cloud, so I don't remember right now whether we're in a state where you can actually get the free tier without even enabling billing. But at least if you enable billing and stay within the constraints, you won't actually get billed. Yes?
I think Google was offering $300 free for a year to just try the cloud.
That's right, yeah.
Which is pretty generous, frankly.
Yeah, so right, if you're brand new to cloud, you can get a healthy chunk of cloud credits. It sounds like it may currently be 300 just to start playing with for new applications. And that would apply to anyone as an incentive to come play. And then again, the cloud credits program that we have for nonprofits and so forth also applies if you decide that you have some more sustained or significant expenditure that is necessary for your research or what have you. All right, so before we leave the world of VM-style computing, I want to take a moment to talk about what you might call kind of phase 2.5 approach. So this is Container Engine or Kubernetes. This is actually much more like how Google currently runs most of our web services, the ones that you use as consumers every day. We're not managing VMs at the low level of something like Cloud Compute Engine. Instead, we're using a system much more like Container Engine, where you define what are called pods in the nomenclature, which is all kind of based around a Docker container or one or more Docker containers that describes how your jobs need to run in cloud. And you can create a kind of virtual cluster and then assign jobs and say, I want 3 of these, and I want 6 of those, and I want to resize that one to 12, and it will worry about placing your jobs within your virtual cluster for you. It will worry about setting up those machines according to your Docker containers. It takes away a lot of the management overhead of actually running jobs in raw VMs. So in fact, the only thing that I ever use raw VMs for anymore is the one that I run to log into and then be able to run manual commands in the cloud environment. For any kind of production use, I actually would use Container Engine, which is just like a thin layer, but a very handy management layer on top of Compute Engine that takes care of what would otherwise be a great deal of management drudgery. So you're still in this model of deciding how many you want and what region of the world you want them in and so forth. So it's not like a fully serverless model, but it's much better than the traditional VM management model, where it's much like you bought 1,000 computers and then had to figure out what to do from there. So Kubernetes is an open source system now. You can invest heavily in this stack and be able to move it to other cloud providers as well. There's just absolutely zero bad things about this plan. Go do that. And as I said, we are using this technology internally. So over the years, we have been working, for example, in improvements to the Linux kernel to support isolation among multiple jobs within a given machine. We launch over 2 billion of these things internally to power every week to power our applications. So this is a seriously battle-hardened technology. All right, it's otter time. So I've been diving a little deep into some of the technologies that you can use most directly with earthengine. Where there's sort of a special tooling on the earthengine side to support that. I'm now going to give a little bit more of a whirlwind tour of several of the other higher level services that you might want to think about using in your computational workflows before finally diving into machine learning, my personal favorite subtopic. So the first of these higher level services that I want to talk about is Cloud Dataflow. So Dataflow is a programming environment for parallel computing, general parallel computing, that's designed to solve both the scalable batch computation problem and the scalable streaming computation problem within a single framework. And this is a much closer to a true serverless environment. This is also much closer to how we internally run big batch computations within Google. It frees you from most of the resource management tasks. It's based on a couple of technologies, as I was alluding earlier. Everything that we're doing is based on some exciting technologies that we've published papers about over the years. So you can go read about Flume and Millwheel as the sort of inspirational technologies. Of course, those papers were published a few years ago, so the technology evolved since then. But you can get a feel for what it's all about. And we've actually been open sourcing, much like TensorFlow, we've been open sourcing Dataflow under the Apache Beam project. And you can think about it as being a little bit like a Spark-like system, if you're familiar with that, except even more kind of mature. If you've been doing a lot of Spark development, it's worth looking at some of the case studies of kind of the amount of boilerplate still required in Spark versus what you can do in Beam. In many cases, it's pretty impressive. And the fact that you can do streaming in the same environment really cleanly is pretty amazing. So the basic model, the programming model here is you have one or more inputs. You describe a sequence of transformations. You're kind of building up a graph of operations that will then ultimately result in some outputs. And there's this library, both in Java and in Python, for building up these graphs, inserting your custom Java and Python processing within any of those transformations. And allowing the library to take care of many of the parallelization issues and join and shuffle and all these sorts of steps that come into play in big data processing. So this is an example of a real-world Python application that in this case is reading in lines from an input file, got a counter here that counts the occurrences of individual words and then gathers them up and writes out the counts. And the point is that this could be run on a huge corpus of words, and it will automatically worry about taking that input file or files, chopping them up into shards, sending them off to individual workers that will count the words within each shard, bring those counts back together in a coherent way, and ultimately write your final counts. And that same set of primitives can be rewired ever so slightly in a stream processing model, where now, for example, you might be doing word counts on a PubSub feed coming in. Say you've got a PubSub feed monitoring your favorite social network feed or whatever, and then you've got a sliding window and you want to run this word counting operation on every 5-minute sliding window. And the way you write the code for those two cases is basically identical. And this allows you, if you're someone who's dealing with kind of the real world, maybe you have a sensor network or something like that in play, to do both your bulk processing of historical data and your on-the-fly processing of new data in the same way. And under the hood, this is actually the technology that we're using to run EarthEngine batch jobs. Just kind of a fun fact. Same core technology beneath each product. Now, you may already have an investment in Spark or Hadoop or whatever, and that's great. They're cool too. They were all also inspired by Google papers. We're not jealous. We are happy to help you run those in Google Cloud as well. And there's a product called Google Dataproc, whose job is to help you set up Spark or Hadoop or Pig or Hive clusters in a turnkey way for you to run your traditional parallel data processing pipelines on the cloud. So this is a great way if you have existing pipelines and you want to get them running in Google's cloud quickly to do that. If you are thinking about writing a pipeline from scratch and you're considering Spark, this is an example of a sort of side-by-side comparison of Spark versus Beam, Beam being the open source package behind Dataflow that is definitely worth a read. Sort of showcasing some of the neat features of Beam for helping simplify your programming model. Another really, really exciting product that we have is called BigQuery. This is a SQL engine for processing large tabular data sets at petabyte scale. And at this point, we're in the realm of the fully serverless system. You just show up with your data and your SQL query, and you go. This is the system that we originally built within Google to manage querying our own logs data. The system called Dremel internally, we published a paper on a while ago. This is Dremel packaged up as a product that you can use as well. So you can imagine the scale of logs data at Google is something ridiculous. And that's the problem that Dremel was built to solve. So if you want to rip through hundreds of terabytes or even petabytes of data with your queries in a short period of time, that's its job. It's got a UI that you can use. You don't need to, but I usually do. That looks like this, where you can write your SQL queries and kind of run interactively, see and explore the results. And it'll do things like, maybe you have 100 terabytes of logs data and you even want to use maybe an inefficient regular expression, something that we can't optimize. We really need to touch every piece of data. And it'll still take 30 seconds to rip over all that because it's really great at just coming up with lots of little shards of work to do and distributing them over a ridiculous number of machines and gathering up the results for you, all without you having to manage anything. Really fun tool. On the conventional SQL side, you can also install, using the Cloud SQL product, a conventional SQL server. MySQL or Postgres are both supported. This is particularly valuable if you're, again, migrating from some existing system that's reliant on a traditional SQL server, or you just have some new application that really is it's a good fit for a traditional relational database. In particular, Postgres Our Postgres offering includes support for PostGIS. If you're not familiar with the world of spatial SQL, PostGIS is really the best-in-class open source implementation of a spatial relational database. So it can do amazing things with spatial data. It's an amazing tool. It's been around in the open source world for many, many years. The one limitation is that it is a conventional relational database. So it's basically fitting on one machine, approximately. And so there are scaling limits beyond which it cannot go. But for many realistic geospatial data processing use cases, you're nowhere near those scaling limits. And for those, PostGIS is fantastic. And the ability to kind of turn on a whole PostGIS system with a couple clicks is pretty great. Moving quickly through the last couple of products I want to talk about here. Cloud Data Lab. This is the environment within which I do most of my cloud work using all the other tools I just talked about. So Cloud Data Lab is our Python notebook interface in the cloud. It's Jupyter, if you're familiar with that. So I can use it to access any of the products I've been talking about. But instead of being at the command line, I'm in a Python notebook environment where I can add notes to myself and chain sequences of operations that I want to run frequently, write functions that I want to reuse. Do interactive data science with all these tools from one portal. So if you take Tyler's Python class, he will walk you through initial setup of Cloud Data Lab with the earthengine SDK installed, so you can get running there. It's been gaining a lot of attention lately as also a really fantastic place to do your development of machine learning models with TensorFlow. I'll have a few more words to say about that in the final section. So the way it works under the hood is your notebooks are running in a little compute engine instance. So they've got some tools that will help provision your VM and run the Jupyter environment there and get all of the permissions and authentication and libraries installed properly and so forth for you to use all the Google Cloud tools easily. It includes an integrated web Git client so that if you've got scripts somewhere that you want to pull into that environment, you just pull in from that Git repo and you can sync back out to it. This is, if what you're using it for is to puppet earthengine and to puppet BigQuery and to puppet Cloud ML engine, and you're not running any of the real computation on it, then you can just use a little bitty like an F1 micro instance, which is the default, and it's either literally free or virtually free, depending on what you're doing. So this is just a fantastic way to manage your work in the cloud. It looks a little bit like this. This is me running a simple little earthengine script inside Data Lab. So these are code cells. I could have text cells. This is an image cell. It's the output of my earthengine script. It's got tools for managing these notebooks. And what's great about this environment is it's just Python on a machine that's a VM, but it's your VM. So you can install whatever you want. So if you need to do like a hybrid of big data crunching in the cloud and local processing using some totally arbitrary Python module or whatever, you can do all that in one integrated environment in Data Lab. Highly recommended. Within it, we have created, and Tyler again will tell you more about this if you take his class, a variation on the standard Data Lab image. So they have an image, a Docker image that is how you kind of get Data Lab pre-installed. We have made a derivative version of that that also includes the earthengine SDK, all packaged up and pre-installed. So if you create your Data Lab instance with this one extra command line flag, the image name command line flag, you will get, in addition to all the usual Data Lab goodness, also the earthengine SDK goodness. And it includes also a notebook that you can use to authorize it as yourself to earthengine. Question?
Can it run on other machines, like download it to my laptop?
Yes, yeah, you absolutely can run Data Lab on local machines. If you go to their website, they have tutorials for how to do a local install of Data Lab. You don't get the benefits of, for example, automatic service account provisioning that you get in cloud, but yeah, absolutely. And if you have other stuff locally, there are certainly advantages sometimes to doing it that way. I don't have anything locally ever, so don't ever do that. All right.
One more question.
Yes.
Storage.
Yeah.
Do you have anything similar to Amazon's elastic file storage?
So I'm actually not super familiar with the feature set of EFS, so I'm not sure how to answer the question quite. We have a couple of options for you to work with. There's within the VMs, you can configure the sort of virtual hard drives to be used with those in various ways. I don't know what degree of elasticity is supported there. And then for ordinary kind of arbitrarily elastic storage, you can use cloud storage, and you can, through some chicanery, mount cloud storage within these VMs. Proper, healthy support for that is, I believe, currently underway. But you can do it using Fuse and sort of open source tools. That may be a closer fit to EFS. All right. Last but not least, let's talk a little bit about TensorFlow and CloudML. And I know that not everyone is super familiar with TensorFlow or this type of machine learning, so I'm going to say a little bit about the types of machine learning that we're talking about here, and then a little bit about kind of where we're at in using them together with earthengine. So TensorFlow rather quickly became the #1 machine learning repository on GitHub when we open sourced it just 2 years ago. It's been an amazing ride to watch. This was based on many years of machine learning research inside Google, where we had been, for our own applications, kind of pushing the boundaries of machine learning. And so we were able to package up a lot of that knowledge into a machine learning library that kind of quickly surpassed its competition. So a few words about how it works. It's really a math library. It's just a math library optimized for certain kinds of math. In particular, certain kinds of parallel math done on what we call tensors. If you're a mathematical purist like I am, your blood boils every time any of these people use the word tensor, because it has a very specific meaning in mathematics, which is a little different from the meaning that they've adopted here, where they just mean generically an n-dimensional array. So it could be a matrix, could be a vector, it could be a larger dimensional object. And then you create a flow graph, a graph of computations to be applied to these arrays, to these tensors. And it's just a math library that's particularly good at certain parallel graphs of operations on tensors, with implementations for running on GPUs and on CPUs. And then also we've been building some pretty amazing specialized hardware accelerators for these kinds of operations that we call TPUs, or tensor processing units. So it's open source, you can run it wherever you like, you can run it totally locally, you can buy a machine tricked out with a whole bunch of GPUs and do pretty amazing model development all locally, or you can run it in the cloud and take advantage of our even larger scale. So what are we really talking about here, though? I mean, artificial intelligence as a whole is a very blurry, generic term that doesn't really mean anything exactly. Sort of the more you poke at it, the less clear it is what it means. Very specifically, this is within the sort of subfield of machine learning, which is mostly about teaching machines to recognize particular patterns that humans often are good at, but in some cases humans are not as good at. And within that, the neural network is a very particular type of algorithm that we've rediscovered in the last maybe half decade or so. This is an approach to machine learning that goes back to, in some cases, arguably even around the 50s. It had a couple of early periods of hype that faded as it became clear that it wasn't actually good for anything besides some toy problems. And then it turned out a few years ago, the math to some degree and also just the scale of computing had shifted, and we were suddenly able to solve some amazing real-world problems using neural networks, and in particular using what we call deep neural networks. So to say a little bit about that, it started mainly with cats. Everything always does around here. we're looking at how can you classify YouTube video and understand what you're looking at there. And still images, the same essential problem arises. It turns out everything is a cat, so that was an easy, on YouTube anyway, easy problem. Anyway, the way these things work is you'll take an image and maybe feed every pixel of the image in as one input in a large grid of inputs. But then there will be, we call it a deep neural network when there are a large number of these layers, where at each layer we're applying some mathematical operations, usually fairly simple, to some weighted combination of inputs from the previous layer. And that's all it really is you combine inputs, apply some mathematical operation, combine inputs, apply some transformation. And if you pick your mathematical functions right, you can get very general ability here to model almost any mathematical function through this. But that's not the interesting part. I can come up with all kinds of ways to write arbitrary functions down. The interesting part is that now we actually figured out how to then work backwards to say how to set all these knobs, this maybe millions of knobs in my parameter, in order to actually recognize a cat versus a dog. And this backpropagation methodology there is where there had been some advances that, combined with computing scale increases, helped us to be able to apply this to real-world cat detection problems. Obviously, cats were featured prominently in some of the blog posts about all this work, but really where we find ourselves using these tools in practice today, we use a lot of them in geo to help map the world. So we're driving street view cars over ridiculous numbers of miles of the road, and a lot of the tools that helped inform TensorFlow's own development really came out of how we were recognizing objects, for example, street signs in those images, how we were pushing the boundaries of machine transcription to understand all of the text on all of the signs we were seeing, all the storefronts we were seeing, all of that. Yeah, definitely a phone call is the right thing for right now. Okay. So, we've been seeing usage of deep learning exploding within Google, just as it's been exploding outside Google. Now, one caveat I always have to say at these moments is deep learning has finally proven that it can be used to solve real problems, and we are in another hype bubble. There's no question we are in a hype bubble. So you have to be thoughtful about what are the classes of problems that this tool actually can solve well. It is amazing in, it's opened up whole new possibilities. And there are some people who imagine that you can sprinkle a little bit of machine learning liberally onto whatever you're doing and it will somehow be magical, and that is not the case. It is essentially a function estimation problem. If you have a lot of data, you can train a model that will be able to estimate that function or classify your data, but you need to have enough training data, it needs to be high enough quality, and we still don't understand exactly what the constraints are on when that will succeed and when that will fail. This is very much a research effort still. But what we do know is that there are a lot of problems for which it does work. And so there's a lot of people looking now at trying to use it and helping to figure out what that sort of bounds of applicability are. We do by now know some of the keys, right? Deep learning, in particular, really relies on having large data sets. For a pretty simple reason, you've got a lot of parameters to tune. And so you need to have a lot of examples, a lot of rich examples, in order to even have enough data to hope to tune all of those parameters. Needs to have a good model, a good basic structure of the neural network. We have discovered by now that some models work much better than others. There are a lot of people who will tell you they know why, and they are wrong in most of the cases, because this is a research field. So as we find models that work well for certain classes of problems, those then get deployed for many other similar problems. And then there are other problems for which we just don't know yet what a good model is. And in fact, even for the models that we think are good today, somebody may discover tomorrow a model that is much, much better and may cause us to reevaluate our idea of what a good model is. So this is where it helps to have a machine learning expert on hand if you're going to dive into machine learning. And because of the large data sets, they need lots and lots of computation. And for all these reasons, this is why machine learning is really made for cloud. The ability to manage large amounts of data and large amounts of computation in one environment is what cloud is great at. It also allows you to job out to Google problems like optimizing the hardware for this kind of math. This is the most recent generation of our cloud TPU, the hardware accelerator for our machine learning models. This is the kind of sort of shared resource that you can take advantage of if you come play with us. So what does this really look like if you're using Google's machine learning offerings? There are basically 3 categories to know about. You can just go get the open source TensorFlow package and run it anywhere. By all means, do that. Publish great papers. This is aimed especially at the ML researcher. On the other end of the spectrum, we have packaged up particular APIs to solve particular problems around machine translation, around speech decoding, around image recognition, around other aspects of natural language processing. If you're building an application that can benefit from some of that kind of smarts, you might be able to use some of these higher level machine learning APIs directly. And we have more of these coming out all the time as we figure out what are patterns that work well. That we can turn into products in their own right. The middle is what gets me excited. This is the cloud machine learning engine. This is a serverless environment for both building models and applying models at scale where they're custom models, your models. It's just like running TensorFlow yourself, except without you having to worry about machines, GPUs, any of that stuff. You just show up with your data and your models, and you go. And as we continue to build and improve upon things like our hardware optimization tools, that's where they're all going to be fed. So if you really want to ride that wave, it's a great reason to go get on board the cloud machine learning engine bandwagon. And data scientists like me are really who this is most aimed at, though you can also use it to run your models operationally if you're building, say, a web app or a mobile app that's powered by some model that you can host in CloudML. I said a lot of these things. Fully managed service, you supply a TensorFlow graph. It'll train at big scale. It'll run online prediction using your model. You can puppet all of this from Data Lab, from that Python notebook environment. So I'm not going to dwell on this, but just to say a little bit about a very common configuration that we're seeing more and more customers showing up with. They've got data either coming in some combination of kind of real-time data coming in through Cloud PubSub, or offline data coming in, entering the system through cloud storage, using Dataflow to do kind of pre-processing of this data. So this is the Python and Java generic parallel processing environment I was describing. In some cases, for legacy reasons, also using Dataproc, which is the Spark or Hadoop sort of variant, especially to do the batch processing. And then pushing this data, processed data, into BigQuery for easy, quick SQL analysis, or into Bigtable, or now also Cloud Spanner to power their web applications. And then finally, once you've got all the raw data, pushing this into our cloud machine learning engine to do deep learning on that data. And what's fun about this entire flow is that this is 100% serverless. No one had to think about a single VM anywhere in that flow. So this is really allowing people to focus on the data science they want to do. Question?
Just to clarify, so are you saying that it also picks the processors to use for like the GPUs versus?
Yeah, I mean, you mean like the CloudML engine? Yeah, there's a knob. Yeah, you can, and there's different pricing based on what kind of processor you want, but you don't have to worry about provisioning them. You can just say, I want to run these on GPUs, or I don't.
Can you give a sense of the pricing?
You know, that's a great question, and I've been using it internally where I get to not care. So I actually don't have a strong intuitive sense for the pricing. There are other people in the cloud world who would be able to answer that question better than I, so I'm going to shut up on that front for the moment.
I think the short answer to that, in a lot of instances, when the GPUs came out and
Yeah, and right, we've been trying to slowly bring all the prices down as best we can, and that's been fun to watch. Anyway, it's a good question. I don't have a great answer. Yes?
From an earthengine perspective,
Yeah.
how does...
Yes, good question. I will get there. Okay, that's on the very next slide. But yeah, okay, serverless everything, great. So now, how might you go about using earthengine and TensorFlow together? Today, the way that people are already starting to do it is the most common flow. It's amazing to see how well earthengine can be used to pre-process geospatial data, take data from a diverse range of sources, maybe slice it, dice it, do some maybe cloud-free mosaicing or what have you to produce a well-structured input that you can then pass to TensorFlow running in CloudML to do your training on your inference, and then take those results and post-process or visualize them in earthengine. So if we look at the previous graph, in many ways, earthengine is analogous to BigQuery, for a very different type of data, but structurally, it's a serverless environment that will store, in this case, geospatial rather than generic tabular data, allow you to do pre-processing and slicing and dicing of various sorts. But then earthengine also is useful even further to the right off the screen in the post-processing and visualization world. And for geospatial data, of course, as we know, visualization is such a powerful component of that data science. So today, one thing that's really fun about using these tools together is that the programming models are very similar, very compatible. In both worlds, you get your head into the same space of writing a sequence of Python operations that are implicitly defining a graph of computation that you want to run that will get run by the system over there, Google, you figure it out. And so they're fun to program together. The way that we literally move data back and forth today is based on staging the data typically in cloud storage in between. This is not beautiful, but it does work. You export your data, your preprocessed data, train and infer, get the results written back to cloud storage, and then import the results back into earthengine if you want. What I wanted to close with is a little information about kind of where we're heading and how you can participate. So what I'm working on right now is more direct integration between earthengine and ML Engine, or really and any other data processing system running in cloud. So backing up a second, ignoring the slide for a moment, earthengine was really designed originally to help you run your analytical operations at scale inside earthengine. And it's been really great at that, but that hasn't quite addressed a different use case, which is people just want access to our data catalog or to our data catalog as preprocessed by earthengine, and they want to pull that data out for processing in some legacy tool or some new different tool like CloudML, some tool that isn't earthengine at the heart of their processing. That just wasn't a use case that we'd originally been designing the API and the system to support. So we're going back and working on that right now, starting with a new API that's currently available in early access that's specifically focused on just querying subsets of data from some earthengine asset or assets. So if you want to run a big pre-processing job, that can be entirely internal to earthengine to pre-process your data. Then either the raw data or that pre-processed data can be queried in blocks on the fly and efficiently. And that would allow then a large job running in CloudML to reach directly to earthengine for its blobs of input data. So that's sort of the first step of the step that's furthest along in terms of was direct integration, sort of a multifaceted effort, but this is the effort that is furthest along. And we're principally, first and foremost, interested in it for this machine learning use case, but we're actually also quite interested in it for other use cases. If you have some other reason that you want to run a blob of computation that pulls data in this way, that is not running inside earthengine, but is running elsewhere in cloud, we're interested. So yeah, let us know if you have a good use case. We're just starting to ramp up this early access program. So the better a fit it is for your immediate use case, the earlier we'll be able to kind of slot you in. But yeah, over the course of this year, we'll get this into a state where you can, from TensorFlow, kind of directly refer to your earthengine assets for at least the common use cases of things like sliding window convolutional neural networks, for example, is I think the top use case. All right, Lemur, and we're done. Thank you all for coming. I'll be around for some questions. And I think there's food or something.
You mentioned convolutional at the end. That's very interesting. One of the issues with that I know is there are often millions of parameters and they can take weeks to train. I've blown up my laptop a few times. Are you going to be often, I know there's a big trend now towards pre-trained networks where you just retrain the final fully connected layers. Is that the kind of thing that might be offered as a classifier in earthengine at some point?
Yeah.
Feature detection and all of that, because that would be super cool.
Right. So I think you're pointing at what is personally a dream of mine. I think the field of transfer learning is evolving fast. Right. So the question is, there's been a trend in machine learning towards approaches where you take a mostly trained network that was trained on some other task that you believe might be related to your task in some way, and then you only retrain the top few layers for your new task. And that means you have many fewer parameters to retrain. And so you potentially could retrain with a much smaller corpus. This could, in principle, be accessible to many more data scientists. And if we can get to that state where that actually works pretty well across remote sensing applications, then I think the idea of packaging everything up entirely within earthengine, much like the classifiers, the conventional classifiers that we have in earthengine today, becomes really interesting. I think the exact structure of that network for these purposes doesn't quite exist yet. The rich pre-trained networks that exist are really mostly designed in this space to handle RGB imagery of cats on the internet. And we need to figure out what are some variations on that theme that will accommodate multispectral, multi-channel data. But I absolutely hope we get there. Yeah, and I believe we will. At least when I'm feeling optimistic, I believe we will.
Great.
You have the microphone?
Yeah, good to know that's on there.
Any other questions? I know I'm between you and your food.
Would that be a good use case for early access?
Would that be a good use case for early access? For doing that kind of research would be a fine use case for early access. Yeah, depending. Right, yes. Those of you who are interested in getting involved in the early access program, reach out to me, let me take your email addresses, let me get a little discussion group going, because I think a lot of you will have shared general interests anyway, and I can keep you abreast of things as they change. In addition to the raw API that I was alluding to, we're also doing some work on how you would actually invoke that from TensorFlow in some sensible way, for example, that don't yet exist, that will exist over the coming couple months, hopefully, thereabouts. And so depending on exactly how well your application maps on to some of the stuff we're already doing, it may make sense for you to actually come in a few weeks later when we've got a few more of the obvious missing pieces built. Yes,
so
Eric.
Don't
worry about it.
Yeah, good. So for working on data stored in BigQuery within earthengine, you must always do the upload. You must always transfer the data from Google Cloud platform to.
True of both, yeah.
Okay, you must always do that transfer, that step of transfer from the Google Cloud storage to.
Yeah, so currently, right, you must always, if you say have image data or table data in cloud storage or in BigQuery that you want to process in earthengine, you have to import it into earthengine as an explicit step. We have been talking with a number of folks who are interested in some alternative models there. The one that is most promising, but that we're still looking into, would be for image data. There's an emerging standard from a consortium of satellite image providers that's called Cloud Optimized GeoTIFF. And the idea here is you have a GeoTIFF where the data is structured within that GeoTIFF in a particular way that is entirely compliant with the GeoTIFF spec, but that actually makes it fairly efficient to pick out an arbitrary block within it. This is very analogous to how companies like us, like Descartes Labs, others who are building their own image databases, build their internal image databases. So it may be that we can get GeoTIFF into a state where it's a pretty reasonable storage layer for interactive querying. Now, what we haven't done is the actual assessment of what are the various overheads involved here, of the GeoTIFF format itself not being really optimized for this. What are the overheads of the data being in cloud storage rather than in our own database where we can precisely co-locate data with computation for you, things like that. So we don't know what the costs are. It's clear that there's some interest in being able to do this. We just don't know whether it's going to end up being so efficient that you're actually going to want it once you know what it looks like for real. Maybe yes, in which case, awesome, we'll go do that. The biggest question we haven't answered is, even if you could access your GeoTIFFs on cloud storage just as efficiently as you can access images in our catalog, the other thing that our catalog gives you is all this indexing of the metadata. And that second half that happens implicitly in like every single shard of our computation is hammering that index to figure out exactly which images are relevant to that shard. You know, that's a critical component of the overall system, and it needs its own solution in a world where the primary data lives in cloud storage. So there's some work to be done, but we are exploring it actively, and I would certainly be curious to hear about your use cases. The usual class of use cases are just people who have large amounts of data and who are concerned about redundant storage costs.
On the command line, when you imported images to earthengine, you first copied it over to cloud storage. Do you have to do that, or can you take things from a system directly into?
Yeah, so if you're just doing like a one-off, a small image, you can use our GUI, which will make it look like it's one step. What's actually happening under the hood is the GUI is uploading the data into a cloud storage bucket and then triggering the ingest. The general problem of efficiently moving large numbers of bytes from wherever you are up to the cloud turns out to be non-trivial when you look at it in detail. The cloud storage folks have really solved that problem, and they'll support parallel streamed uploads and all these things. And rather than focusing on reinventing that wheel, we're focusing on using their solution there. So if you just have a small thing, do it through the GUI, it'll all be hidden from you. But for big data, the cloud storage staging area is going to be with us at least for a while.
Walk me through like a case example. Let's say if I wanted to have on-the-fly stretching of Landsat data with a web interface, what services would I need to employ to provide that?
Sure. So there are a number of ways you can do it. By far the simplest, the one that models how many small apps powered by EarthEngine have been built, is to do it with just two services. And I actually didn't even talk about one of them today. Well, the one is EarthEngine, as the place that actually would do the storage of Landsat, the stretching, and the map tile creation, and so forth. And the other, which was actually the original Google Cloud Platform product, is App Engine. And it's in some ways isolated from the other cloud tools, which is why I didn't really talk about it much. But it is the simplest place to just put a full web app together on the web, where you can host the GUI, the JavaScript and HTML, and then you would use typically the Python App Engine backend, from which you could use the Python EarthEngine library to actually control the processing that you wanted done. So that's a totally serverless, two-component solution to your problem. If you want to get, for some reason, fancier than what you can do with App Engine, that's when I think I would move to Container Engine as the sort of power tool option, where you could then manage, but in a fairly easy way, a cluster of web servers that were powering your application, and you can stick a load balancer in front of that and serve out serve the public from there. But unless you have a reason not to use App Engine for your website, I would use App Engine for your website. It's just, if all you're trying to do is run a website, that's, they're a powerful, like, I believe, I'm pretty sure that Snapchat is still App Engine based. It's a pretty powerful web hosting environment.
Has there been any improvement for the tools for bulk loading, like lots of imagery into the earthengine system, and then also in the reverse direction? I think I thought I caught you saying that the image export had some sort of feature where you could, in a single task, push out multiple images, not the tiled one.
Yeah, okay, so great, good questions.
And also, could you do that for tables too? That would be super convenient for us.
Do which for tables?
So like in a single task, fairly long running one, be able to dump, hundreds or thousands of little JSON objects out to cloud storage to drive a web app.
Sure. Okay, all good questions. The short answer is I don't have great answers to some of those use cases. If you need to upload lots of images and manage the metadata on them and so forth, the best tool that exists for that, which uses the Python API, is the one that Gena made and shared in the open source world. It does just manage a large number of upload tasks. It's going to be, however you slice it, one upload task per image that you're ingesting. It's just a convenience wrapper on top of that. And if you hit any limitations with it, it's not a super complex tool. It's a thin wrapper on top of our upload API, and you could modify that to suit your needs. The export, multi-TIFF export that I was talking about is just about one giant image where you can control the tiling more flexibly. We've been talking for a while about basically an image collection export, and that's on the list. In the meantime, much like it's one task per uploaded image, it's one task per exported image, and the best bet is just to use the Python API to submit those tasks. We have lots of users who are kind of pushing the boundaries of running lots and lots of batch jobs, which is fun and fine. Practical advice is, in general, if you're going to do more than 10,000 tasks, it's best to write a system that can kind of slowly feed them in, say, batches of 1,000 or a few thousand at a time, and kind of let the previous batch finish before you start the next, just to avoid things going sideways without you catching it. But then the last question about table export. So there, we don't even really have, within our API, a good idiom to express a table of tables. So I would be curious to hear more about your use case. You might want to try coming to office hours sometime this week and talking to someone about that. But my initial thought is that your better bet might just be to structure that as one export that exports one giant table, followed by something like a simple data flow job that chops it up if what you need for some reason is lots of small tables. It's a fun excuse to go learn the data lab or
Really
a data flow Python API.
What I'd need is to be able to get at, just have high availability to some index in that table, for a web app.
Sure. So then the question becomes, maybe rather than storing it as files, actually putting it in a cloud-hosted database like Cloud Spanner or Cloud Bigtable or the App Engine Data Store. There are a lot of cloud databases, and in fact, one of the biggest challenges there can be a sort of paralysis of choice to understand which is the most appropriate for your application. If your application is simple, then often the answer is a lot of these would do fine, and there's not going to be a good reason to pick one or the other.
So what about directly accessing the vector tape, the vector store that's in the earthengine?
Yeah. So right. Great question. If that would work for you, then first of all, if you can compute them on the fly, you can already do that today. But if what you want is to be able to pre-compute, then I think the pieces that you're missing, if you want to just query it out of earthengine, are all coming pretty close. Right, so today we announced the ability to upload your own shapefiles. Hot on the heels of that, anyone who's paying any attention can figure out would be the ability to just materialize a table back as an EarthEngine asset. Because you can already export and import. So it's just dorky that we don't yet have a one-step loop for that. So then you'd have the table in EarthEngine, and you could use the existing EarthEngine API to just query the data out. And that's reasonably efficient. And we've got some optimizations coming. So we have internally some applications that we're looking at using an EarthEngine asset to power a web app directly. We aren't designed primarily as a serving table. We're designed for computation. So that means that we aren't systems that are designed for serving will try to make themselves be very simple in terms of the queries they support in exchange for super low latency. And that's how you can get down to the tens of milliseconds. We're going to be more like the hundreds of milliseconds system that can do a lot along the way in those hundreds of milliseconds if you need it to. So if half a second response time is fine for you, then yeah, that might be a fine option. Thank you all for coming.